Hello Bite-Sizers and welcome to this Bite-Size Bio web seminar. I'm Nick Oswald and today's sponsors are MacMod Analytical, who provide reliable, high-performance chromatography columns and competent, responsive technical support. You can visit them at www.mac-mod.com. Today's presentation is titled Exploiting HPLC and UHPLC Selectivity with Rational Stationary Phase Design, and it's being presented by Alan McKeown, who is Business Development Director at Advanced Chromatography Technologies. He has vast experience in chromatography gleaned over many years in pharma, and we are delighted to have him presenting today. As always, we'll have a question and answer session after the presentation, so please type any questions that you have into the questions box, which appears on the right-hand side of your screen, and I'll put them to Alan at the end. So let's go over to Alan for the presentation.
Okay, thank you, Nick, for the kind introduction, and welcome to everybody to this webinar. My name is Alan, and I work for ACT, who make the ACE range of HPLC and UHPLC products. Today's seminar is on exploiting selectivity and the importance of selectivity in HPLC and UHPLC, and also today's seminar will give you a bit of an understanding into how we design stationary phases. What are the things that we think about when we're designing stationary phases, and what type of properties do we look for? So selectivity, why is it so important in chromatography? Today I'll talk about that theoretically and also practically. I'll talk about some phase design concepts, and I'll focus specifically on the C18AR and the C18PFP and how we design these stationary phases and why these give advantages to the chromatographer or the method developer. I'll also briefly mention UHPLC with the ACE range of products. This is one of the most important equations in chromatography, the resolution equation. This equation can help us as chromatographers when we are developing our methods or screening our samples. Resolution is important. This is why, as chromatographers, we support many colleagues in formulation, chemistry, and many other fields. Many people give us samples and they want to understand what's in those samples, and they also want to normally understand how much of those different things are in those samples. Resolution is therefore very important. Now, resolution from the resolution equation is made up of three main parts. There is an efficiency term, a selectivity term, and a retention term. Just by looking at this equation, it is not clear which is the most powerful term in that equation. However, if we look at the equation in this way, with this graph that was published a long time ago now, back in 1999, we can understand the relationship between each of those components and resolution. And it's clear to see from the graph that selectivity alpha has an almost linear relationship with resolution. It's a very powerful term. Now, of course, efficiency is also an important term in chromatography. Quite rightly, as chromatographers, we want very good peak shape. We want nice narrow peaks. This helps us with sensitivity and helps us with integration. But if we look at the graph on the screen at the moment, you can see that as the relationship between efficiency and resolution goes up, it then plateaus off slightly. Maybe not as powerful as alpha or selectivity. Now, for retention, this is also a very important term in chromatography. If we don't retain our compounds, we cannot separate them. So K is a very important term in chromatography. However, if you look at the graph, and we were taught, all of us many years ago, as part of our chromatography theory, for a K value of greater than 10, you can see there is limited payback in resolution. So no matter how much longer we leave the components onto the column, we don't improve the resolution very much. But we have to retain our compounds in order to separate. So hopefully you can see from this graph, selectivity is very powerful. Now, there are many factors that affect selectivity, and on the slide now are a range of different factors, many of them mobile phase element-based factors that can have an effect on selectivity. And I've listed them. Values at the bottom have a smaller impact on selectivity, and as we go up the list, the factors have a larger impact on selectivity. And you can see at the top there is the column stationary phase for the left-hand side of this slide for isocotic separations. Now in gradient separations, of course, we have to consider all of these parameters too, but we also have some other parameters such as the gradient steepness, the apparent K, dwell volume and column dimensions to also think about when we're developing our methods. But all of these things that I've listed on the slide here, column stationary phase, still floats somewhere near the top as being one of the most important ways that you can affect selectivity. Now on this next slide, what I've done is we've done some separations in our lab to show the effect of different bonded phases, different stationary phases on this simple separation. This is a separation of 5 basic analytes in isocratic mode at pH 6, and we started the analysis on a C8 column, an ACE C8, and then we took the column off and we equilibrated a C18 column, and we did some injections. Then we took the column off and we put a C4 column on and did the injections again. Same mobile phases, same system, same samples. And you can see pretty much you get what you would expect. When you move from a C8 to a C18 column, there is an increase in retention time for these components. When you move from a C8 to a C4 column, there is a decrease in retention time for these components. So for these 3 stationary phases, the dominant mechanism of interaction is hydrophobic interactions between the analyte and the stationary phase. You can see for all 3 chromatograms, the evolution order stays the same. 1 through 5, 1 through 5, and 1 through 5, because the mechanism is essentially the same. Now, if we change the mechanism on the stationary phase, the mechanism of interaction between the stationary phase and the analyte, we start to see some differences in the chromatography. So now we do the same analysis again on the right-hand side of the slide with the cyano column and also with a phenol column. Now, a cyano column is dominated by dipole-dipole interactions, and the phenol column is dominated by pi-pi interactions. And you can see from the chromatograms on the right-hand side of this slide, we now have a change in the elution order. So we are using selectivity. We are moving peaks around in the chromatogram so that we are seeing a different elution order. For the cyano column, this is 31542, and for the phenol column, this is 13245. And this is important because if this was a mixture that we were analysing as part of a method development activity, we would want to make sure that we see everything in our samples. That is the step 1 of any method development activity. What have you got in your samples? Step 2 is then to optimise your method. And you can see from the right-hand side of the slide there, we've got these different elution orders, meaning we're moving the peaks around the chromatogram. Now, the phases that are on the screen at the moment are based on a very pure silica. The ACE silica is a very high-quality silica. And the principal contaminant that you get in many silicas are metal ions, particularly older style silicas. Now, these metal ions are not good for chromatographers as they give you detrimental secondary interactions. And you will see this in your chromatogram as peak tailing. Peak tailing isn't helpful for the chromatographer because it makes it more difficult to integrate those peaks, and it's also not as good for reproducibility. Reproducibility is something as chromatographers that we want to get with every single method development activity. We spend our time developing methods, and we want to make sure that if we run that method again, once we validated it, we're going to get the same chromatography. So reproducibility is really important. And in fact, reproducibility and column lifetime are 2 of the major factors for analysts or chromatographers all around the world. And the data on this slide is from a survey performed by someone called Ron Majors, who you may have seen. He writes an article every month in LCGC. And every 2 years or so, Ron does a survey out into the chromatography community where he sends out a questionnaire of lots of questions to chromatographers. And one of those questions that he asked is, what are the most important things for you with your columns that you buy from many different manufacturers? And for the last 5 years, so the last 2 surveys or so, chromatographers have said column reproducibility and column lifetime are really important to them. Why? Well, in the major industries like the pharmaceutical industry, food industry, healthcare industry, hospitals, and so on, when people develop methods, those methods rarely stay in the same place. They may move to a different lab or a different facility, into manufacturing or quality control groups. And so making sure that once you develop a method, that it's very reproducible and that it will meet your system suitability criteria every time is really important. So you want to make sure that if you buy a column today or next week or next month or even next year, if the method goes into manufacturing, you could be buying columns for the next 10 years. You want to make sure that every time you run your chromatography on that column, you're going to get the same elution profile, the same chromatography as you developed. And also column lifetime is important for chromatographers too. Columns are consumables, but they're relatively expensive. So you want to make sure you're going to get more than 50 injections out of the column. Ideally, you want hundreds or thousands of injections out of the column. So long-term performance is also an important variable. Now, looking at the data from this publication from ROM this year, it's interesting to note that reverse phase chromatography is the most dominant separation mode that people use in various industries around the world, and that's maybe not a big surprise. Looking at the details of the survey, it's interesting to note that C8 and C18 columns are the most popular columns that people use. 60% of people use those type of phases in their separations. Then it's phenol column at 16%, then cyanose and fluorinated columns. And in fact, 92% of analysts use a C18 at some point in their working week. So this is a very, very popular stationary phase. Everywhere around the world, people use C18 columns more than any other type of column. Why do they use that stationary phase more than any other? Well, maybe some of the reasons why is because C18 columns from most manufacturers are pretty reproducible, column to column, batch to batch, and also most C18 columns give pretty good lifetimes too. So these are a very popular stationary phase for these types of reasons. However, I started this talk talking about how important selectivity was in chromatography. If we understand and exploit selectivity, we really can hit the ground running in our method development. The thing is that most C18 columns have limited selectivity. They're pretty similar to each other. And in fact, on this slide, you can see where I have 4 manufacturers, C18 columns from 4 different major manufacturers. And this is a separation that we did in our laboratory. It's a 5-minute gradient method, 16 components, small molecules. And what I'm trying to highlight on this slide here that is pretty much the selectivity is quite similar between these columns. So for the ACE XL, the elution order is 1 through to 16. For the water's acuity, it's 1 through 16. For the non-mets kinetics, 1 through 16. And the adjuvants or Vaxiclips, 1 through 16. Pretty much the elution order is the same. And yet we make our silicas differently, we bond them differently, we end cap and we pack them differently, and yet for this type of mixture, a wide range of analytes, we're still getting a very similar elution order. We're not getting much differences in selectivity. The selectivity is very similar, and yet selectivity is the key to resolution. So at ACT, what we said is that we wanted to engineer new stationary phases that have alternative selectivity, but with the robust properties of a C18 ligand, because that's why it is so popular and most chromatographers will use a C18 or start with a C18. We want any stationary phase we design to be reproducible, that goes without saying, column to column, batch to batch, year to year, and we want very good lifetimes out of any phases we develop too. People expect and they demand a good number of injections from the columns that they buy nowadays. All of the ACE phases are based on a very inert, pure silica. And that's important because it gives very good peak shape, so we get very good efficiencies. And also, we want any new phases we design to have very low bleed in the UV, and also low bleed in the MS. And this is important because you will have seen bleed from stationary phases before. In the UV, for instance, when you execute a gradient, you see a rise in the baseline as the percentage bleed increases. And sometimes this rise in the baseline can be hundreds of million absorbance units high from the start of the chromatograph. Now, if you're trying to integrate small peaks at 0.1 or 0.2% level on that rise in baseline, that's very difficult. And also for in the mass spec, so if you're developing LCMS methods, you will know if you see bleed. You'll very high background in your mass spec total line chromatogram, and you can also get signal suppression and variable ionization in the mass spec source. All of these things lead to poorly reproducible methods, or LCMS methods, or LCUV methods, and that's not what you want as a chromatographer. Also, we want any phases we design to be usable in 100% aqueous eluents. So more and more we are now seeing people using very high aqueous or high buffer containing mobile phases as they're analysing more and more polar or mixed polarity samples. And of course, any phases we design, we want them to be available for HPLC and UHPLC particle sizes. Many people now have screening systems set up using the power and speed of UHPLC, but many QC and manufacturing groups still use 3 micron or 5 micron HPLC type separations. So it's important that there's a scalable range of particles available in any particular phases we design. Now, we looked at many different types of building blocks from a material characteristic perspective and also a chromatographic characteristic perspective. And it was interesting to note that ring systems with aromatic functionality, so such as phenyl and PFP type ring systems, can give you very good advantages in terms of their interactions with analytes. So they can offer you unique interactions which can give you alternative selectivity to C18 columns. This is very good, selectivity with the power and the key to resolution. Many ring system-based stationary phases also give you enhanced retention of polar compounds. This is also very useful. And many aromatic functional group based phases can be used in 100% aqueous or 100% buffer eluents. They don't suffer from the phase collapse or poor de-wetting phenomenon that C18 columns do. The thing is about these ring system-based phases is they do have some disadvantages. Many of them can suffer from really quite bad phase bleed, which, as I said before, is not good from a chromatographic perspective in the UV or the MS. And also, some of these phases can have batch-to-batch reproducibility and robustness that is weaker than the C18-based stationary phase, which is what we're holding as our gold standard. We want the characteristics of any phase that we develop to be like the very popular C18 stationary phase. So why are these aromatic functional groups so interesting? Well, predominantly one of the main mechanisms on these ring systems are pi-pi interactions. And these pi-pi interactions are special and they're unique to these ring-type systems. These are a type of electron donor and acceptor interaction that originates in the pi systems in the unsaturated areas on the analytes and the stationary phase. And it's that interaction that gives them unique selectivity. Now, the thing is these type of pi-pi interactions can be manipulated depending on the type of substituents that you attach to the ring system. So you can actually maximize the orthogonality or the differences between stationary phases as part of phase design. So let me explain that with, for instance, a phenyl ring, a simple phenyl system. This is actually a weakly electron-rich ring. The electrons are pushed into the ring by the alkyl chain spacer that attaches through the siloxane band down onto the silica. Now compare that to a PFP ring, which has those big electronegative fluorines attached to the ring system, and those electronegative fluorines want the electrons to come out of the ring and attracted to the fluorine, and that actually makes the ring slightly electropositive, and that is very different to the phenyl type ring system. So we have two complementary but unique type ring systems here that we can use in our stationary phase design. So let me show you that in pictures. So here we have a simple benzene or simple ring system, and if we substitute that ring system with electron donating groups, and I've written some on the slide there, and I'm using a phenyl group as an example, you can see we have a weakly electronegative ring system with a weak dipole across that ring. And we can compare that to if we substitute onto the ring electron withdrawing groups, such as the very electronegative fluorine. And you can see that those electrons are drawn out of the ring, creating this strong dipole moment and also a slightly electropositive or electrodeficient ring system. Now, these type of differences in the properties of these rings are your classic pi-pi interaction. This is an interaction between an area of low electron density and high electron density. Now, that's all very interesting from a material perspective, but we are chromatographers. So what does this mean for us as chromatographers? Getting back to the core subject. Now, what we've done at ACT is we have combined the robust properties and the hydrophobic mechanism of a C18 type ligand, an alkyl chain ligand, with the characteristics and mechanisms of a phenol type ring system into a single product called the ACE C18 AR. This contains the mechanisms of both C18 and a ring system in a single stationary phase. And on the other side of the slide, for the C18 PFP, again, we've combined and created and brought together the properties and the mechanisms of the C18, the hydrophobic mechanism of interaction, together with the ring system properties of a PFP ring into this unique product, the ACE C18 PFP. And these are both two products that are unique to ACT. And we think they give chromatographers an advantage when they're starting their method development. Now, important for me to say about these two products, because I've been asked this question previously, is what we haven't done, what we have not done is combined two containers of the C18, for instance, and a phenol, for instance, and into a physical mixture. So this is not a combination of two stationary phases, because we would still have the disadvantages of the phenol stationary phase. The C18AR and the C18PFB are individual ligands that are chemically synthesized and then attached to silica through the siloxane bond in a single step, which is then end capped and packed into columns. So this is not a physical mixture of two stationary phases. It's a single unique ligand, each of them are single unique ligands. Now, these new stationary phases are based on very pure silica, the same silica we use across the whole ACE range, which is very high quality, gives very good peak shape. And these two new stationary phases are available in HPLC particle sizes and also UHPLC particle sizes as the ACE XL. And what we're finding, the more we work with these phases, the more the chromatographers out in different industries work with these phases, is these multiple modes of interaction, so the hydrophobic mechanism plus the different ring mechanism interactions are really making a difference for people when they're starting their method development. These different mechanisms are giving people the power of selectivity when they're screening their samples or starting their method development activities. So let's talk a little bit about mechanisms. So what type of mechanisms are present, for instance, on the C18AR stationary phase? So at ACT, we use a variety of protocols to understand the chromatographic properties of the stationary phases that we make. And predominantly we use the Tanaka protocol, which is a series of different probes that you run under specific mobile phase conditions, and it gives you an indication of the weighting of different mechanisms on the stationary phase. This is a published protocol, published a long time ago by a scientist called Tanaka, and it's an established protocol for understanding mechanisms on chromatography stationary phases. So now on the slide you can see that I've highlighted 5 different separation mechanisms: hydrophobicity, pi-pi interactions, dipole-dipole interactions, hydrogen bonding, and shape selectivity. There are 3 different columns highlighted now on the slide. So for instance, for a typical C18 stationary phase, and when we characterize the typical C18, you will see that the data revealed to us that the C18 is dominated by hydrophobic interactions. Hydrophobicity is the dominant mechanism on C18 stationary phases. That's no great surprise. We would all guess that. So obviously more crosses means that mechanism is more dominant. Maybe what everyone doesn't realize is that most typical C18s have a little bit of shape selectivity to them. And that's due to the length of the alkyl chain and the bonding density of the C18 on silica. Now, your typical phenol stationary phases actually have low hydrophobicity. And the reason for that is many phenyl ring stationary phases are attached to the silica through a small alkyl chain spacer. So that means you have low hydrophobicity on most phenyl stationary phases. But of course, what the phenyl stationary phase brings to the party, so to speak, is it brings pi-pi interactions. And you can see there's 3 crosses there for pi-pi interactions. There's a weak dipole interaction, a little bit of hydrogen bonding, and also some shape selectivity as well. Those planar rings and the way they're attached down onto silica afford some shape selectivity. Now, with the ACE C18AR, we wanted to combine those mechanisms of those 2 phases together. And when we characterize the stationary phase, the C18AR, you can see that all of the hydrophobicity is present. There's a strong hydrophobic interaction element to the stationary phase. Plus, we've preserved the ring mechanisms of this stationary phase too. So the pi systems and the pi interactions are there, weak dipole, hydrogen bonding, and also the shape selectivity is there too. So what we're seeing with this characterization table is that these multiple modes of interaction are present on this new stationary phase. This should give us an advantage when we're developing methods or screening samples. So let me show you that now chromatographically. So on this slide, I have a simple mixture of substituted nitrobenzenes. So we have the trinitrobenzene substituted species, the dinitrobenzene, the mononitrobenzene. Now, toluene is present in this mixture as a hydrophobic marker. So the retention time of toluene tells you how hydrophobic a stationary phase is. And this is the standard material that we use in many of our tests to give us an indication of hydrophobicity of the stationary phase. Now, if we look at some physical and chemical properties of these 3 analytes in particular, we can see if we look at their log P values, so log P is a measure of lipophilicity, you can see that the trinitro substituted species has a log P of 1.2, the dinitro species has a log P of 1.6, and the mononitro species has a log P of 1.9. So if we were to analyze this mixture on a standard C18 column, we would expect the retention and elution order, because these are simple molecules, to be related to their log P values. The higher the log P, the more it would interact with the stationary phase on the C18 because it's a hydrophobic interaction, and so the longer it will be retained. And when we did the analysis, that's exactly what we found. So you can see here peaks 1, 2, and 3 relating to the nitrobenzenes, and then you can see out here toluene as peak 4, marking the hydrophobicity of that phase. Now, these analytes are actually pi acid analytes, so electrons are being drawn out of this ring by these nitro groups. If we look at the pi acidity of these stationary phases, these analytes, their pi acidity is related to the degree of substitution. So the more these nitro species are substituted on the ring, the more pi acidic is the analyte itself. So you can see there's trinitrobenzene, dinitrobenzene, and mononitrobenzene. And the trinitrobenzene species is the most acidic. Now, if we analyze this mixture on a phenyl stationary phase, the most pi acidic should interact the most with the phenyl pi systems on a phenyl stationary phase, meaning it would be retained the most. And when we analyze this mixture on a phenyl stationary phase, that's exactly what we found. So you can see peak 1, which is the most pi acidic, now interacts the most, and so elutes the latest in that series of trinitro, dinitro, and mononitro. Now, interestingly, you can see here that toluene is eluting much earlier, and that is because most phenyl phases have a smaller spacer than obviously a C18, and so the hydrophobicity of this phase is much less. So toluene marking the hydrophobicity of the phase, you can see it elutes much earlier. Now, with the C18AR, what we were trying to do is combine together the interaction of a C18, the mechanism of interaction of a C18 and the phenyl ring together in a single stationary phase. And when we analysed this mixture on the C18AR, that's exactly what we found. Now you can see we still have the reverse solution order here, so the most substituted nitro species interacting the longest with the pi systems on this phase. So you can see that the pi systems are the stationary phase. And then toluene, marking the hydrophobicity, has moved from around 9 minutes here in the phenol phase, where there's a low hydrophobicity, further out to nearly the same attention time as it was on the C18 stationary phase. So we can see there's increased hydrophobicity of that phase. So we've blended together the hydrophobicity and the pi systems in a single stationary phase. So what about the C18 PFP? So this is a similar discussion for the C18 AR, where we have the same 5 mechanisms, and we characterize 3 different stationary phases: the typical C18, the typical PFP, and the ACE C18 PFP. So starting from the typical C18, as I said before, dominated by hydrophobicity with a little bit of shape selectivity. Now a PFP, the typical PFP stationary phase, also has low hydrophobicity because many of the small alkyl chain linkers that attach the ring to the silica particle through a siloxane bond are much smaller than the C18, so there's low hydrophobicity on these phases. But as with the phenol stationary phase, you can see we have pi-pi interactions, which aren't present on the C18. We have quite a strong dipole moment on the PFP stationary phases due to the electronegativity of the fluorine, and the fact there's 5 fluorine groups around the ring. There's hydrogen bonding, and also shape selectivity, which is an important mechanism on PFP phases. When we characterize the C18 PFP, you can see that we've retained all of those mechanisms of interaction on that stationary phase. So again, hopefully demonstrating these multiple modes of interaction are present. Now the shape selectivity and isomer resolution power of the PFP phase is very interesting. And in this particular slide, we've got a mixture of substituted methoxybenzene isomers. Now you can see that we have various methoxybenzene isomers here. So we have 1,2,3 trimethoxy, 1,2,4 trimethoxy. Over here we have the 1,3,5 trimethoxy. Then the dimethoxybenzene isomers, 1,2, 1,3, and 1,4, and then the monomethoxybenzene as in the mixture as well, and then toluene as a hydrophobic marker. Now, looking at the physical chemical data, you can see that it's not as easy to predict retention for many of these species because many of the values are very similar. So the log P is related more to the degree of substitution of, it's related to the degree of substitution of the rings, and their pi basicity isn't really related to the position of the substituents on the ring. But this is an interesting mixture because it will show us the positional isomer or regioisomer resolution strength of PFP stationary phases. So when we analyze that mixture on a standard C18, as you would expect, we get extensive correlation with many of these species. And you can see toluene here marking the hydrophobicity of the stationary phase. Now, ACE don't make a small chain space of PFP. So for this example, we've used a Hypersil Gold PFP. And you can see when we did this separation, that's actually not a bad separation. That shows you that power of even of the PFP ring, even with a small spacer chain between the ring and silica, there's almost complete resolution of this mixture and all those components. There's a slight correlation here, a slight correlation between peaks 5 and 4 here. But you can see the reduced hydrophobicity of the stationary phase, peak 8, toluene, eluting in the center of this crowd of isomers here. Now, when we analyze this same mixture on the C18 PFP, we can pull that retention back out because now we're bringing hydrophobicity as a mechanism back onto that stationary phase, as well as the other mechanisms of the PFP, and we get full separation of these methoxybenzene isomers. So the C18 PFP shows a very powerful positional isomer and shape selectivity terms as a phase. I've talked a lot about selectivity and a little bit about phase design. How do you know what selectivity you have when you're doing your separations in your lab, or how do you know what differences between stationary phases are and which stationary phases should you start with? Now, there are many protocols in the literature and in the published and peer-reviewed literature you could look at. I've picked up this one because I think it's really interesting because it's a very simple approach. It was devised by this guy down here called Uwe Neuer. This was published in 2006. Now, what Uwe Neuer came up with is an S value, an S index term, or a selectivity descriptor term, and it's derived from this simple equation. And the way that you get the R squared value for this equation is you take analytes of interest to you. The more analytes, the better. It makes the model more robust. And you run them on a particular method on one column, and you know the retention times. And it's the important thing here is that you know the retention times of your analytes. Then you take that column off. You use the same method, the same elements, the same samples, and you run the mixtures again on the second column, column 2, and you know the retention times. And what you do is simply plot the retention times on column 1 against the retention times on column 2, and you draw a line, a regression line, through the points. You get an R squared value, which you put into the equation here to determine your selectivity value. So here are the data that we use in our labs when we were looking at the selectivity value for the C18 PFP versus the C18, the ACE materials. So we use 100 analytes, 102 analytes in our training mixture. It's a mixture of acids, bases, neutrals, different pKa's, different log P's, different shapes and sizes, with a molecular weight up to around 550. When we plotted those data against each other, we got an R squared value of 0.9888. And when you plug that into the equation, it gives you a selectivity value of 10.6. With selectivity terms, we deal with whole numbers, so this is a selectivity value of 11. So what does that mean? What does an S value of 11 actually mean? Well, S values into the high teens, into somewhere between 20 and 30 are good. And what that means is that columns that you're looking at are suitably different to each other. So if you were to run mixtures down these two columns, you would hopefully see the peaks moving around in the chromatograms, meaning that you could see everything in your samples. So what we did at ACT is we ran a C18 column versus the C18 PFP in a methanol containing mobile phase, and we got an S value of 11, which is this value down here. We then ran the C18, the same mixture on a C18 PFP versus the C18 AR, and then the AR against the C18. And you can see we've got 3 different S values here, 10, 11, and 12. What we then did is we changed the solvent to nitrile, and we reran the mixtures again. So we ran the mixtures on the C18 and on the PFP, C18 PFP and C18 AR, and we've got 3 different selectivity values. Now, these values, as you can see, are a bit smaller. So why is this important? Why am I showing these values? Well, what these values give you an indication of is the selectivity space you're exploring. The higher the values, the greater the selectivity space you're exploring. Now, the power of this approach is that you can look between 2 different solvent systems. So now we can plot the retention times on a C18 in methanol versus the retention times on a C18 in acetonitrile, and we get a higher S value, and now an F value of 50. And we can slowly plot the data between the 2 solvent systems, and we can come up with different S values. And you can see those S values are growing all the time to an S value there of 19, which is when we ran our mixture, that is the mixtures run on a C18 and acetonitrile versus the mixtures on a C18 PFP in methanol. That's our most orthogonal combination. I've taken exactly the same data that was on that slide and put it into tables here. So here's the methanol plane, column 1, column 2, and the selectivity value. The acetonitrile plane, column 1, column 2, the selectivity value. And then the solvents plotted against each other with the different columns giving you different selectivity values. And you can see there the top value that we achieved was an S value of 19, which is pretty good. If we were to run sample mixtures down this type of combination, this would mean we would be moving the peaks around the chromatogram. We'd be using selectivity to make sure we see everything in our samples, in our chromatograms, and making sure that we can see everything. Now, why am I showing you these values? Well, I get asked many times, how do I do method development? And I've been to different places where some people use just one column, typically a C18, and they will do all their method development on a C18. And I've been to many companies where they have a dedicated platform with 6 columns or 8 columns, many different mobile phase evidence, and the instrument is running for 24/7 days at a time, generating a lot of data. Now, both of those approaches are valid, but what I'm trying to show here is if you understand selectivity, you can make the right column choice at the beginning. So you could take, for instance, I've used 3 columns here, and I understand the selectivity space that I'm exploring with those 3 columns. And so what I've developed here is a very simple method development screen. By understanding selectivity, understanding the columns in my screen, I can understand the selectivity space that I'm exploring for those different ranges of small molecules. The selectivity really is very important, and hopefully you can see from these 3 phases, I can understand the selectivity space I'm exploring. So I've talked about the C18AR and the C18PFP. What type of analytes are these tertiary phases particularly useful for? Well, the C18PFP I've listed on the slide here. These are examples of recent applications that I've been working with people on where we've got very good separation with these types of molecules. Not forgetting, of course, that the excellent shape and isomer resolution power of this particular phase. That's probably one of the biggest features of this phase, as well as the other mechanisms that are present. And this is a nice example showing that regioisomer selectivity. In the top chromatogram here, we have a C18 based separation. And in this particular example, the chromatographer was interested in separating the meta-parachlorinated species. With a standard C18, they couldn't achieve that resolution. And with a C18AR, where you would perhaps expect a bit more interaction, we still couldn't achieve that resolution. But under the same conditions, the C18PFP was very powerful with its regioisomer selectivity, and we were able to pull those 2 peaks out quite convincingly and very satisfactorily. So for the C18AR, we have these are lists of different types of analytes that we've had success with recently, helping different chromatographers separate different types of compounds. Not forgetting that C18AR does have some shape selectivity. It's moderate in its nature. It's not as heavily weighted as it is on the C18PFP, which is very powerful for shape selectivity and isomer resolution. This is an example showing steroid analysis where the separation on a standard C18, this is obviously HPLC mode, we have correlation of some of these peaks, the critical pair peaks here. When we try this separation on a phenol, we then began to get other correlation between different peak pairs. So bringing those 2 mechanisms together into the C18AR, where we could use hydrophobicity and the ring systems of the phenol type group together, we could achieve full separation of this steroid mixture. So very useful, very powerful. So I've talked about selectivity. Now, what about UHPLC? UHPLC is the evolution of chromatography. It's something that we all see perhaps even on a daily basis. And if we can combine selectivity with the power of UHPLC, we've got a very powerful tool for method development and sample screening. So ACE is the UHPLC column format provided by ACT. And this is a very high efficiency silica based on very inert 2 micron silica particles, which are suitable for use at 1,000 bar. All of the selectivities that ACE offer are available, including the 2 that I've told you a bit more about today, the C18AR and the C18PFP. These phases are highly reproducible, and that's important. We spend a lot of time designing these phases to make sure that the reproducibility, column to column, batch to batch, and also particle size to particle size for scaling is very, very good. The robustness of these phases is also important. Many chromatographers told us they wanted very good, robust UHPLC phases, so we spent time and effort making sure the phases we designed and commercialized are very good in terms of their robustness, and I'll show you some data on that in a minute. Now, the 2 micron phases we developed have actually, when you pack those into a column, they actually give you quite a low back pressure, especially when you compare it to other sub-2 micron materials. And that's because what we've done is taken a tight particle size cut of the 2 micron. The particle size distribution is quite narrow, and also this allows us to use different frits, larger frits, and that also helps to reduce the column back pressure. Why is that important? So hopefully that means you reduce the shear on the particles in the column, and hopefully that will help you, the chromatographer, with your column lifetime. Now these 2 micron phases are fully scalable with the HPLC range, and of course they're useful and can be used on any commercial equipment. So this is a nice slide to show column robustness for the A6L UHPLC column. This experiment was done at 1000 bar, where we did 2000 injections, 2000 gradient runs, and every 100 injections or so we did an isocratic efficiency assessment. And that's important because isocratic efficiency assessments really tell you truly how your efficiency is changing across your run. Gradients assessments are not valid. The isocratic assessments are the way that you should look at efficiency across a column lifetime. And here are the data that we developed. On the y-axis here we have the percentage of initial efficiency from when we started the run. On the x-axis here we have the number of injections. And I like showing this slide because what we're trying to show here, this is the early days when we were developing the technology and the UHPLC phases. And you can see that in the early days we realized we would have to change our hardware, the way we pack these columns, to make sure we got the robustness of this stationary phase, and for the columns for UHPLC type pressures. Now we're in a situation where anybody who gets an A6L column gets this type of performance from their system. So this is, you can see here, 2000 injections with very, very little change in efficiency across the lifetime of that particular run at 1000 bar with gradient analysis, cycling up and down gradients. Very robust phase. This is a good slide as well to show scalability, so the mixture of acids and neutrals in this particular slide, which is important. And you can see the retention characteristics, obviously the elution order, and the selectivity, the peak spacing between these particular peak pairs is very, very good, from different particle sizes all the way through up to 10 micron. Obviously different bondings here, different packings, different columns and so on, showing that the variability between these different particle sizes is pretty low. Should be very helpful for people who need to scale between different particle sizes. Now, I just want to mention another word on this low back pressure, because this is an interesting feature which chromatographers have been talking to us about for a little while now. So this is a separation we did in our labs, 13 component mixture, 5-minute gradient analysis. And you can see we get a Pmax, so we're using methanol in the separation, of 364 bar. So we repeated this exact same analysis, but on a waters column, a phenomatics column, and an actual column, same dimensions, same analysis, same sample, same level phase, elements, everything the same, except we took the column out, equilibrated the next column, and repeated the run. And you can see there's quite a significant difference in the pressures here. So between the AC and the waters, there's over 200 bar pressure difference. It's 540 here and 540 here. So that's a significantly lower pressure, which we think is helpful for chromatographers. So hopefully it will help with column lifetime. Now, of course, the sharp-eyed amongst you in the audience will note this is a 2 micron particle. The waters is 1.7, the phenomena is 1.7, and the adjuvant is 1.8. And you're absolutely right. We would expect some differences in the pressure, slightly higher pressures on these three down here, because their mean particle sizes are smaller. Physics tells us that if the particle size is smaller, then the pressure will be higher. But I still don't think, I'm sure, hopefully you'll agree that you wouldn't get over 200 bar difference, for instance, here. And that's also because this is a 2 micron, and it's a reasonably tight 2 micron particle, we can use larger frits as well. And those larger frits also help us reduce this pressure. And we think this is an advantage. We think this is useful for chromatographers. So this slide is a simple gradient type separation to show the scaling of separation from a 5 micron situation, ACE 5 micron C18 here, and taking it down to the A6L 2 micron C18, so scaling that separation from HPLC to UHPLC type separations. You can see now we go from 25-minute runtime to sub 5-minute runtime, which is very helpful. But what we've done in the next step is that we've used the power of selectivity, so we can change the peak spacing here. We can make sure we meet our resolution criteria greater than 1.7 by switching to a C18 PFP type column, 2 micron, and we've really ramped the flow rate up. So now we're at a very high flow rate, very high pressure, and you can see you get a sub 1 minute type separation. So really just trying to show if you really push the separation like this, you can get these very rapid, very quick separations. Now, we would not ordinarily recommend these type of conditions. This is just an illustration to show you how fast you can go with the power of UHPLC. And in the next step, you can see the very high throughput, high productivity type separations, which is one of the features of UHPLC. So this is a nice slide showing you why people are so interested in UHPLC. So just bringing that all together now and coming towards the end of the seminar, hopefully you've understood why selectivity is so important to chromatographers. I talked about it theoretically in the beginning, and I showed you the relationship between each of the components in the resolution equation, including selectivity. And why selectivity with its almost linear relationship is very powerful. I also talked a bit about stationary phase design and how aromatic rings have these unique properties that are different to a standard C18. And they're useful, they are helpful for us because it allows us to have alternative selectivity for our separations. And selectivity, it should always be step one in your method development process or your sample screening. I talked a bit about how we designed the C18AR and the C18 PFP and how these stationary phases are unique but they're complementary. The combination of the hydrophobic interaction mechanisms and the ring mechanisms on these stationary phases really do offer the chromatographer advantages for method development. And also I talked a bit about the fact that these phases are available and fully scalable for HPLC and UHPLC formats. And these phases will meet the demands of the modern chromatographer in terms of reproducibility, robustness, low phase bleed, and they are all based on a very pure silica, which gives you excellent peak efficiency. Now, the phases I've talked about today, there's a lot more data on these phases, the C18AR and the C18 PFP, and there are separate information and brochures available on these phases, things like stability, applications, which I haven't had time to talk about today. Those are available if anybody is interested. And we also do free guides for ATP. So this guide is about 60 pages, and it's a guide to the analysis and purification of proteins and peptides by David Carr. And this is a guide to LC and LCMS buffer selection and a HPLC troubleshooting guide written by John Dolan. All these are about 25 pages each. All these are free guides, and they're available if people are interested. And here is the website address where you can order some of this information, or obviously you can email me directly as well. So I wanted to say thank you for coming to this seminar and attending this seminar today. I hope it's been useful for you. And the main message that I want people to think about when they walk away from this seminar is think about selectivity. It's a basic concept in chromatography. It's one of the most powerful. And if we use selectivity, it means that we can make the right column choices, the orthogonal column choices for your separations in your labs. And that means that when you start that method development activity, hopefully you'll hit the ground running, you'll see everything in your samples, and then you can optimize your method in a very efficient way, in a very productive way from there. Thank you for your attention. I'm happy to take any questions.
Thank you very much, Alan. That was a really interesting seminar. I wish I had that when I was in the lab doing HPLC. So we've got a few questions in from the audience, a couple here. I think you might have actually covered some of them, but it'd be good to go over them again. So the first question is that you mentioned that contaminating metal ions in the silica can cause peak tailing. How does this work mechanistically? Is that known?
Okay. Is it possible for me to see the questions, or will you just read them out and I'll answer them there?
I'll read them out if that's okay with you.
Yeah, that's no problem. So the way that so metal ions. So let me start at the beginning. So there is an older what's called type A silica, and these are your traditional materials that are made such as spherosorb and spherosorb, ODS, and materials of that type. Probably about 15 to 20 years old and greater now. And these materials have a variety of metal ions that could be in the hundreds to thousands of parts per million present. And it's a variety of metal ions that are present, things like iron and aluminium, and essentially those are contaminants from the solvents that are used in the manufacture of the silica process. Now, when those silicon materials are made and then they're bonded and so on, some of those metal ions are present within the network of the silica particles, and also some of them are present near the silica surface. Now, the silica itself has silanol groups. This is the SiOH group present all over the silica, because silica is essentially a siloxane, an Si network, and those metals are present within that network. And what they actually do is they activate the silanol, the SiO group, to an SiO minus, and they make it a highly acidic group. They make that silica, that silanol, that SiO minus, highly acidic. Now, what that does, what it means is that silanol, that O minus, looks up, so to speak, metaphorically, into the mobile phase, out into the mobile phase element. And if there are any analytes that go past with any type of positive charge or positive dipole, even through electrostatic interactions and dipole type moments, you will get an attraction between that highly acidic silanol and the analyte as it moves past. Now, the reason why you get tailing peaks is because the kinetics of that interaction are different. So there are different types of silanol present on silica. There's a metal-activated silanol, which is highly acidic. Then there's called geminal silanols, vicinal silanols, and free silanols. And all of these have a different degree of acidity. And that acidity is related to the kinetics of that interaction between the positive elements of the analytes and the SiO minus. And that kinetics is different with those different types of silanols. So having metal present means you get highly acidic silanol groups which hang on to your analytes for longer, which means that the peak gets splurged out, so to speak. You get those very deleterious secondary interactions, which gives you a long tailing peak. And that's how peak tailing occurs with silica.
Thank you very much, Alan. That's a superb explanation of that. Okay, so I think we've got time for two more questions, maybe. So first up is, so if I switch from a C18 column, a conventional C18, to one of the ACE columns, what would you recommend doing for method development? Would you recommend starting with the same mobile phase to develop the method and taking it from there, or go back and start the method from scratch, develop a method from scratch?
So this is one of the classic questions I get asked all the time, is how do I do method development? And what I've tried to show today is I've tried to show a very simple three-column, three-bonded phase, two-solvent system method development activity. Now, you can use one column. The simplest form of method development is where you have one column, one temperature, one mobile phase in A and B, and you essentially try and develop your method from there. So maybe you vary just the gradient, the shallowness or the steepness of the gradient, and try and pull your peaks out that way. That's the simplest way you can do it. As you have different parameters and different, so for instance, you look at two different solvents, or you add two columns, you start to add complexity to your method development activity. What I've tried to show today is hopefully people understand that using a single column isn't the best way for you to do method development. Unless you know for a fact, of course, that your analytes or mixtures will separate on that C18, in which case, I guess you're not probably doing method development, you're doing method verification. What I would suggest is that people use a standard system. They do a 5 to 95% gradient. Mobile phase A, typically something like ammonium 20 millimolar ammonium formate. Mobile phase B, probably methanol, something like that. They do a 5 to 95% gradient at 40 degrees, and you see what you get. And then you can change the gradient or even change the temperature, and you start to change the elution profile of that system. In an ideal world, for most people, I recommend try 2 columns. Whichever columns people choose. Of course, it would be great if they chose 8 columns, but I'm a realist and realise that people use lots of different brands. What you need is 2 columns with different mechanisms of interaction, ideally. So a C18 and maybe something like something with some pi systems, a phenyl. In ACE terminology, we recommend the C18 and the C18PFP or the C18AR because you've got those multiple modes of interaction there. But don't do, which I see this quite often, and this is something I try and tell people not to do, is they try and do a method development activity on a C18 column from brand A, whatever that is, and it doesn't work, so they reach into the drawer and they get a C18 from brand B. And hopefully you're seeing from the selectivity plots that I showed today, C18 versus C18 will give you an R² value of 1, which when you put it into the selectivity equation gives you a selectivity value very close to 0 because you're not using selectivity. C18 versus C18 is not ideal. Try and change the mechanism if you can.
That is a great call, Alan. Well, basically I spent 2 years comparing C18 and C18, so that answers the problem that I was having the other.
Okay.
Okay, so we can squeeze in one last question, and that is you showed that the lifetime of your ACE columns are excellent. What is the cost of those compared to a conventional C18?
So this depends on. So I realise this is a webinar, so this is global as well. So it depends on which country you're from. So I can only speak about really about the cost in the UK.
Or so just relative to C18.
Yes. Yeah. Yes. So the C18 phases are very so the ACE phases are very competitively priced. We price them towards the lower end of the C18. If you imagine C18s as a range, the ACE phases will be pretty much in the middle towards the bottom half of the price range. They're very competitively priced, wow. And we do that because we offer these phases to try and compete against some of the very big boys in the chromatography world, and we know that we have an extremely good product, so we are keen for people to try these. Many people who try the ACE phases then go on to buy them and remain persistent customers, which is great. So we're very happy for people to try the ACE phases. We think they're very competitive. In most markets around the world as well, they will be competitive, although I can't comment on individual territories or countries because it is specific to those territories.
Sure. Okay. Thank you very much for that, Alan, again. And we'll wrap up here now. So thanks again for a really illuminating presentation. I think we've all learned a lot today. And thanks also to our sponsors, MacMod Analytical. And finally, thanks to you guys, the audience, for taking the time to attend and listen in. If you've enjoyed the seminar and you'd like to view the video recording of the session, please visit the seminars page on bitesizebio.com, and it should be available there within the next 24 hours. And there you can also see the other webinars that we've lined up for you over the coming months. So until next time, good luck in your research and goodbye from all of us here at Bitesize Bio.